Thank you, everybody, for choosing my talk as one of the talks that you're going to watch during these few weeks. My name is Marcos, and I'm going to talk about how to build an agnostic model from an embodied simulation. So let me start with just a little issue that we might encounter in cosmology that I think gives rise to the need of these kind of models. So let's assume that we have like the latest state-of-the-art model for cosmology. And let's assume that this is a hydrodynamical simulation, right? Which I think it's a fair assumption, right? Then let's say that this simulation spans a set of results, right? Like spans a space that I am actually showing you here as this moon-shaped contour. And this is basically the space spanned by this set of hydrodynamical simulations, right? Now we know that even though they are state-of-the-art and they have like all of the physics that we kind of know put inside, they also have like some problems, right? So they basically are based on some assumptions that we get from I don't know, observations or from even like theoretical background and so on. And also they are like not exact in the sense of like they might depend on subgrid physics that they're actually not exact. So when we're going to compare them against like the real universe, in the worst case scenario, it might happen that actually they have nothing to do with the true universe, right? Since we made so many approximations to actually have like such big volumes, it might happen that actually the true behavior of the universe is not connected with the simulations that we have. In the best case scenario, at least one of them actually will enclose like the true universe, but only under some like given parameters, and we don't know which of those parameters are actually the true one, right? So, okay, if this is the case, if we try to use these simulations over some, to constrain cosmology, then we will find some biased results, right? Because the physics are not well captured. So what we need is actually some model, some theory that actually does not depend on the specifics of the galaxy formation, right? And actually in the literature, we have such a model. And this model is perturbation theory, right? So only based on theoretical background and on analytical computations, we know how to describe the very large scales of our universe, right? And that's why I have put this perturbation theory encapsulating parts of the simulations and parts of the true behavior of the universe, right? Because it is not able to describe the full set of observations or the full set of simulations. It's only able to recover the largest scales of them, right? Okay, so this is very good, but the problem is that it doesn't make use of the full information that we have. So what we are really looking for is actually a theory that is agnostic in the specifics of the galaxy formation in the same way as perturbation theory, but that is also encapsulating the full set of observations that we have, right? And of course, this should also describe perturbation theory results, simulation results, and also, of course, like the true behavior of the universe. Okay, so how are we going to build such a model? So we're going to build such a model around two main ideas, okay? One that gives the precision that we need to go to smaller scales, and another one that gives the versatility that it needs to actually explore many different solutions. Okay, so the first idea, this idea that is going to give us the precision at all scales, right, from large scales to small scales, is the idea of advection. Okay, and advection is just the mapping between Lagrangian or initial conditions space into Eulerian space, which is the space of where the particles end up, right? In this case, I'm thinking about dark matter particles mainly. And this advection is going to be given by an embodied simulation. Okay, so we're going to use the mapping between initial conditions to the final positions of the dark matter from an embodied simulation. And this is given through the so-called displacement field, okay, which is like the vector field that actually connects these two spaces. Fine. So this is going to give us like the precision of an embodied simulation, right? But now we don't want to assume anything about galaxy formation physics. So what we're going to use is a bias model, okay? And this bias model basically connects the density field of galaxies with the density field of matter, okay? In a functional form. And this functional form can be as free as you want. And the one that we're going to be using is actually the one given by some analytical estimations from perturbation theory, and more specifically, this Lagrangian space expansion bias, okay? And this is going to be given by something very sensible, okay? So this is going to tell us that the more density, linear density there is in the region of space, the higher is the probability or the weight of finding galaxies there, okay? So that's like the first step. And this is this first term that I'm showing you here, okay? This linear B1, let's say. But it is not only going to depend on that, because actually, because of the Galilean symmetries and you know, like these translation symmetries of the universe, actually you can make it dependent on many other things, right? And actually higher powers of this density field are also might actually have like some contribution to this galaxy density field, right? And therefore we include like higher powers of this density field. But not only that, also the tidal field might be very important. So we include the tidal field, okay? And not only that, it might happen that, you know, there's like some smoothing effects, there's like some physics that we don't really get, like due to baryonic physics, for example, that actually can be encapsulated in higher derivatives of the density field, like the ones that I'm showing you here. So we stop here at what we call second order, right, in delta, and that's what we're going to assume for this connection between galaxies and dark matter. So we have the dark matter given by an embodied simulation and the galaxy given by some bias expansion prescription. Okay, another way of seeing this, another way of understanding this, which actually I think is quite pictorial and quite useful, is to think about this as a bias, as a basis expansion, right? In the same way as we think on quantum theory, right? In which we select a basis, and then with that we can actually span all possible solutions for our wave functions. So in this case, instead of having a wave function, we have a galaxy density field. Okay, here I'm showing you the Bose sample galaxy density field, and we're going to check if actually this density field can be described as a combination of some basis fields, right? Some basis terms. In this case, we're going to have the combination of the dark matter density field, okay? Then the dark matter density field weighted by the linear density field. Then the dark matter density field weighted with the square of the linear density field. The same thing, but with the tidal field. And the same thing, but with the Laplacian, right? So the higher order derivative terms. Okay, so, and the idea is that the combination, the linear combination of all of these fields has to be general enough to give you all possible galaxy densities that you can have, right? Within your true universe, right? Okay, so we do this, but there's a big problem, right? Which is, in order to get the precision required, we need an embodied simulation. But embodied simulations are very slow, right? So we need a lot of computational power to actually compute them. So they are not suited for analysis like Markov chain Monte Carlos or Hamiltonian Monte Carlos, right? Any kind of statistical analysis that we want to do over cosmological parameters. So what we do is actually we we accelerate them in 2 steps. One, by accelerating embodied simulations through the scaling technique introduced by Angulo and White in 2009. And once we have that, we can compute the relevant statistics we want to explore, and then input those into a neural network, and then ask the neural network to interpolate between them, right? So we do that, and we find a neural network that can actually evaluate one such a model in about 40 milliseconds. So plenty of time, right, to do your Markov chain Monte Carlo. Nice. So does this work? That's the question. And the first thing that we try to answer is it working at the 2-point level, right? Everything I've said until now was at the field level, except for the neural network, right? That interpolates between whatever statistic that you input. But yeah, let's stick for now at the 2-point level, and then we can explore maybe like other statistics. So at the 2-point level, it works amazingly well. Okay, so we can go from the largest scales, as I'm showing you here, to the smallest scales, at least as small as about 0.7 h of a megaparsec in K. And we recover perfectly well, like some set of data. But I mean, but the fact that you can fit the power spectrum doesn't mean that you're getting the correct results, right? Because you might be fitting it for the wrong reasons. So we go to the cosmological space and we check if we recover the true cosmological parameters. And the answer is yes. Within 1 sigma, which is what we will expect, we recover these cosmological parameters. For example, in this case, like omega matter and the Hubble constant, and also the amplitude of initial conditions, like well within the 1 sigma region that we were looking for. So amazing, right? It works in real space. But sadly, not everything is in real space, right? If you try to focus on, for example, things like spectroscopic surveys, then you know that you're going to need to account for redshift space distortions, right? Like the velocities of the galaxies, right? They're going to input like some shift into your measured redshift, right? And that is going to distort the positions in the way that I'm showing you here in these two pictures, right? This is like from real space to configuration space, which is having like these redshift space distortions. So one has to account for the velocities of your galaxies. Now, how do we do this in this framework, right? So what we do is we include this effect at the level of the displacement field. So now the displacement field of the embodied simulation is not going to be only one mapping the initial conditions to the final positions, right? But it's going to add like this little bit of shift due to the velocity at those final positions. Okay. Now this shift, how do we include it? So what we do is actually we define the velocity in 2 steps in the following way. So we define the velocity as the velocity of the main halo, right, of the halo, if the particle that you're looking at, if the tracer that you're looking at belongs to a halo. And then it will put the velocity of the dark matter particle if it doesn't belong to a halo, okay? So with this, we will capture actually the cosmic flow. We will capture the velocities, well, large scale velocities, right? But not only to the linear level, like the Kaiser effect does, but also to the non-linear level, because halos actually have some non-linear effects on their velocities, right? So, okay, so we will have those, but we know we're missing one component, right? Which is like the intra-halo velocities. So the velocities of the galaxies within the halo, right? So galaxies actually have velocities with respect to the center of the halo. And how do we model that? So the model will actually be something very simple, just convolution with a function, right? And the function that we choose for this is an exponential function. We do that, and then like we can actually see this as these 2 steps that I'm showing you here. So we are in real space. Then we include the central distortion, this what we call the central distortion, which is these velocities of the halos, right? And then we see how things are starting to be distorted in this direction, right? And then we include this intra-halo velocity through this convolution, and then we see how things actually get way larger distorted. This is actually enhanced so that you could see this, but you get kind of like the idea. And again, this is at the field level, right? So in principle, we could do all kind of statistics with this, but let's focus on the 2-point statistics. Does this work? And the answer is yes, it does work. And actually, this is more complicated than in real space, right? Because you're including more information about your velocities. And it works amazingly well on the monopole, quadrupole, and hexadecapole of your power spectrum. And you can see here that, for example, like we get completely results which are completely indistinguishable from the data down to scales of about 0.6. We stopped at 0.6 because we were including a smoothing, right, on the density fields to account for the size of the halos in Lagrangian space. But the truth is that it is unclear how much can we push this, at least at the level of the 2-point statistics. Okay, and does this work also at the level of the cosmological parameters, right? Like, does it provide unbiased cosmological parameters? And the answer is yes. It provides unbiased cosmological parameters, and a different case, right? So a different k maxes, different scales. So if we stop at k of 0.1, then we get unbiased 0.2 again, down all the way down to 0.6. And actually, this is very interesting, right? Because we can start answering the question on how much information there is on these small scales, right? By including these ones. And the answer, for example, for this specific sample, which is, which is actually a sample very close to the Bose CMAS sample, because the number density is actually very similar to the one of Bose, and the redshift is also very similar to the one of Bose. Then we get the following results, which is that, okay, going down from 0.1 to 0.2 in omega matter, there's like a great deal of information. But if you push towards smaller scales, yeah, there's a bit of information down to 0.3, but from 0.3 on, it's kind of like the same thing, right? There's not much information about omega matter at those scales for this model. The same can be said from H, roughly, right? But it's not true for sigma 8. For sigma 8, we see that actually we can push towards smaller scales, right? So this is the conclusion, basically, that we have a model that is able to explore the smaller scales with, with unbiased cosmological parameter estimation, and that can start exploring the amount of information encoded in those scales. So thank you very much, and I hope we can discuss about these things during the meeting.